Okay, welcome to the 15th video in Introduction to Quantum Field Theory, free scalar fields. In this video, we will take the Lagrangian density for a real scalar field phi, and then we will derive the Klein-Gordon equation from this Lagrangian density. So let's look at what the Lagrangian density is. So the Lagrangian density for a real scalar field phi is, if this curly L 1/2 partial mu phi superscript partial mu phi and then minus m squared phi squared. This is the Lagrangian density. How did we derive it? How does it exist? Well, we'll talk about that in a later video, but for now we're just going to assume we already know it. There are two main terms in this Lagrangian density. The first term here, this is called the kinetic term. And this one right here is called the mass term because it has mass in it. So this is called the kinetic term because it describes how the field moves, and this is called the mass term because it describes how the field disperses due to having a mass. We can derive the corresponding equation of motion using the Euler-Lagrange equation. Which if you don't remember, you should go back and watch those videos because they're pretty important for understanding what comes next. So we'll be considering the Euler-Lagrange equation, which is that the partial change of the Lagrangian density with respect to the field minus the gradient of the change of the Lagrangian with respect to the gradient of the field is equal to 0. Granted, when we worked with this equation last time, we had this on the other side, so we just had this is equal to this, but we can move it over and say that it's equal to 0, and it's the exact same equation. So now what we need to do is plug in the Lagrangian density. So there's going to be a factor of 1/2 that just comes out to the very front because of this factor of 1/2. And we get the derivative. I'm going to just write this shorthand, this d phi. I'm going to write this shorthand as d phi of d mu phi phi minus m squared phi squared. So that's the first term, or that's the first term in this equation. So it's this term right here. Now we're inputting this minus the gradient of, now this is the same kind of notation I'm using here. I'm saying it's the derivative with respect to the gradient of phi, of d mu phi, or partial mu phi, minus m squared phi squared. Okay, so that's the first step. Now the next step is to actually carry out derivatives here. The easiest derivative to carry out will actually be this one, because this is the derivative with respect to phi. There's only one term here that that depends on phi, and that's this term right here. These depend on the gradient of phi, so not on phi itself. So we have 1/2. Excuse me, something's in my throat. Um, then we have this term will go to 0, and you'll have a 2 come down here, cancel with this 1/2. So you have 2 negative 2 m squared phi, like this, then minus 1/2 gradient of all of this stuff right here. Which is just equal to, you have the 2's cancel out, so you have minus m squared phi, and then this term. So now what we need to do is focus on simplifying this term, which can look a little bit messy, but just to kind of emphasize, we have the Lagrangian density. We are taking the derivative with respect to the gradient of phi, and then we are taking the gradient of this whole thing. So to do this, we can notice that first off, there's a gradient of phi here, but it looks like there's also a gradient of phi here. So how do we take the derivative of both of these quantities? Because one is superscript and one is subscript, and we're taking the derivative with respect to the subscript. Well, this is where you have to use some tensor mechanic knowledge. So let's just go to the next line. And we need to recall some property. There's a property that we introduced at the very beginning of this series in one of the first few videos. And that is that if you have some quantity a mu, then that's the same thing as introducing the metric and then describing it as a what you call it, as a subscript, as a covariant tensor rather than a contravariant tensor. So we're going to do that for this. So we have minus 1/2 gradient of derivative with respect to the gradient of phi of the gradient of phi. And then we have the Minkowski metric, and then another gradient of phi minus m squared c squared. Now, because we're taking the derivative with respect to the gradient of phi, I'm going to just ignore this term because it goes to 0. So we don't have to keep rewriting it. So that goes away. That becomes 0. But now we have a Minkowski metric in the middle of the equation. And the Minkowski metric is like a constant. It can be moved out. So we can ignore it. So we can get that this is equal to minus m squared phi minus 1/2 the Minkowski metric. Then the gradient. Now I'm going to start using square brackets with respect to this of d mu phi or partial nu phi. So we have successfully turned this into a lowercase, um, what do you call it? A lowercase derivative. So now what we're going to do is we're going to use the product rule to expand this. So just to recall the product rule. Product rule says that if you have the partial derivative of a and b, let's move that. Yes, there we go. Then that's equal to partial derivative of a times b plus a partial derivative times b. So this is the product rule, and we're going to use it. Minus m squared b minus 1/2 Minkowski metric partial mu, then get partial some mu phi of this plus okay, so we now have the derivative with respect to the gradient of phi of the gradient of phi, and then the derivative with respect to the gradient of phi of the gradient of phi, but with a different index. I might have repeated myself there because I just hit my elbow super hard against the chair, and it hit my nerve, and that distracted me for a second. Did not feel good. Uh, Here I need to make sure. So I'm looking at my notes here, and I noticed that I miss a minus sign at some point. So I'm trying to make sure that uh, I got the minus sign correct. Yeah, no, cool. There we go. That's just a weird thing that I just got the sign wrong for some reason in my notes. But that's okay. We can continue. Nothing. The math does not change. I just got a sign wrong at some point because I copied it down incorrectly. But going back to what we were doing, we now want to change this index nu to an index mu to match with this derivative. So we need to use another property from tensors, and that is that a mu is equal to this. So we introduce the Kronecker delta, whereas the Minkowski metric allows us to switch between contravariant and covariant tensors. This allows us to switch between, or this Kronecker delta allows us to switch between different indices. So we're going to use this. Actually, I'm just going to copy this. And this last term is going to be expanded out. So you get a delta mu nu, or rather nu mu and then this, nope, I'm dumb, mu, 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 like this, using this property over here, we get this. But the Kronecker delta is also like a constant, so we can just take this, move it back here, move it in here instead. And then we can move to the next step and actually cancel out these terms here because the derivatives here just go to 1. We get this plus this just goes to 1. And moreover, we can use this property again here to rewrite this partial mu as a partial nu. So now we have two of these partial derivative or two of these d nus, and we have a Minkowski metric here. So we can then move this Minkowski metric back in, and then so we have a -1/2. We have a -1/2 partial mu of the Minkowski metric, or 2 times the Minkowski metric, phi, and there's a factor of 2 here because we add this to it twice. Well, the 1/2 and the 2 will cancel, and the Minkowski metric will change this d nu into or superscript d mu. So we get d mu of d mu, or minus, there's a minus sign here, of phi, like this. And this is a quantity that is equal to 0. So we can now just say that this quantity, the negative of it, is also equal to 0. And what we do is we pull out the phi and have it equal to 0. And this right here this is the Klein-Gordon equation. So it tells us how a scalar field evolves. Now, this might seem like a new equation, but we've actually already covered it. In fact, I recommend that the next videos you watch should be videos 6 and 7, as they cover the dynamics of this equation, which is just a wave equation. Now, I will note that there is an error in videos 6 and 7. There's a part where I say that the phase velocity is slower than the speed of light, but what I actually meant to say was the group velocity. Now, if you don't recall what that is now, then go watch those videos, and in the next video, I will have a correction to my errors in that video.